Which of the following set can be recognized by a deterministic finite state automaton? The first one, the numbers 1, 2, 4, 8 up to 2 raised to n written in binary. Hence, the language that our finite automata should accept is 1, 2, 4, 8 up to 2 raised to n. Let us see whether a DFA is possible for this particular language. For that, we need to first see the decimal equivalent of a binary number. For that, let's consider the decimal format of a binary number. As you can see, there is a common sequence which is 1 followed by 0 or more zeros. Here there is no zeros, here there is 1, 2 and so on. Hence, a DFA can be drawn as follows. This is my start state, which I will call QS. Now, when I get an input 1, it will move immediately to my final state. The reason I'm saying it's a final state is because 1 is accepted. Similarly, if I get a 0 after a 1, then it will still remain in my final state. In this case, even 2 zeros, 3 zeros, 4 zeros and infinite zeros will be accepted by this DF. However, the moment I get a 1 after the sequence of zeros or 1 after the first one, it is not valid because it will no longer be in the form of 2 raised to n. Hence, on a transition 1, I will move to a dead state where a 0 or 1 will go into an infinite loop and it will never be accepted. Now what will happen when I get an input 0 in my start state? For that, let's see what happens when 0 precedes 1, 0 precedes 2 and so on. Does it change the value of 1? No, 1 remains the same. Similarly, does 0, 0 change the value of 2? No, it remains the same. Hence, it is negligible or doesn't matter how many ever zeros come before 1. Hence, 0 will go into the start state itself, forming a self loop. Thus, a DFA is possible for this question and hence this is my final answer. Now, just because A is the right answer doesn't mean we should not see whether B, C and D are wrong. Let's check out why they are wrong in the first place. The second question is the numbers 1, 2, 4, 8 up to 2 raised to n written in unary. Let's check whether DFA is possible for this question. In the unary system of numbers, each decimal number can be represented only by zeros and hence the term unary. Thus, as you can see, 1 is represented by 0, 2 is represented by 2 zeros and so on. Now how do you draw a DFA for this particular question? One might say this is a solution for this question. Let's look at the language generated by this DFA. As you can see, the language generated by this DFA is 0, 0, 0, 0, 0, all having the cardinality 1, 2, 3 respectively. However, is this what we want? No, we want a recurring pattern where the numbers go up to 2 raised to n, that is 2, 4, 8 and so on. 3 is not accepted, 5 to 7 is not accepted. However, since DFA has no stack in the machine, it is not possible to calculate how many zeros are present and hence this question cannot be the answer and B is wrong. The third question, the set of binary strings in which the number of zeros is the same as the number of ones. How do you tackle this question? So first I draw a column where n of 0 and n of 1 tells me the number of zeros and number of ones respectively. Let's take the first case where the number of ones and number of zeros are equal and they are 0. In this case, the DFA is accepted as long as there is no input. That means zeros and ones are equal, which is empty. Now let's assume the case where The number of zeros is equal to number of 1, but exactly 1. In this case, we can have two possibilities, that is 0, 1 and 1, 0. This can be represented by a DFA as follows, where the first statement gives me an input 0 and it is negated when a 1 comes, giving me the final answer, and the same for 0, for 1 and 0. Using the input as 2, we get more possibilities as seen. Here there are 4 options, 0011, 101001 and so on, each which are negated as 0 and 1 comes, which gives me the final state here. But how long do we keep going on for this? Since there is no way again to count how many states are required, this is not a finite state or a finite automata, it's an infinite state, and hence this cannot be solved by a DFA. Now for the set 1, 101 and so on, we can draw DFAs for each of the strings as follows. Here I have drawn for 1, 101 and the same repeats for the rest of the strings. However, one might very well argue that this can be a solution, a DFA solution for the above set. However, firstly, 1 is not accepted by this DFA. I agree 101, 1101 are all accepted, but along with them, this DFA also accepts strings which are not equal in length in 1. As you can see this issue, you are not able to count how many ones before and after the zeros. The reason, as I stated before, DFA does not have a stack, and hence this is not a DFA sum. In fact, this is the set or the types of sum for PDA or push down automata.